Hey guys, welcome to science for section 4.1. But remember I told you I was going to go over go over the chapter 3 review with you guys today. So I do want to go over that with you. Make sure you pull it out, please. I'm not going to go over everything with you though. And honestly, I'm kind of disappointed in this chapter because it would have been really good to go through it with you, but seeing as I didn't have my book in the States, I let you guys go on without really knowing what the themes were because I didn't have my book and I didn't really want to bother Miss Ashley for asking for the pages. So I never thought to ask one of you guys for the pages, but honestly my brain wasn't in the right state of mind when I was taking care of my mom. So I did not realize that this chapter was very in depth, but it's okay because while you may have been so mad at me for the chapter 3 review because it's a little confusing, it's good for you guys because remember I'm teaching you guys a class like this for many different reasons, but the benefits to you guys is I made sure you guys had a book this year, okay? Because you need to be getting used to reading academic textbooks. You need to be getting used to that I'm not going to give you all the notes, that I'm not going to digest the information for you, that I'm not going to process the information for you. And that's why I'm doing it this way. That's why I made sure that people from my church donated these textbooks to you guys this year, not the school, because we didn't have the money for matriculation for these books. I made sure you had this book. I made sure that you had the world geography book because you get information from me when I'm digesting the information for you and making it simple to understand, or making it not simple to understand, but more basic than what the book is going to talk like. But the book gives you so much more benefit in the fact that, yes, you're not going to process all the information. Yes, you're not going to understand everything that you read. But you're going to have the diagrams and you're going to have the terminology that they're using, the technical language that they are using. And you need to get used to that. So in the university, I told you guys this story before. Dr. Paul Gale, one of my heroes of life, honestly, for just him as a person and then his work and then how he got where he was. I'm sure all of you guys don't know who Dr. Paul is, but the guy, the doctor from Anthony's Key. He's also the music minister over at the Baptist Church down the hill. He's done a lot in the community, president of the Doctors Association and everything like that. Well, he said when he was in the university, the teachers did not teach the material. The teachers told them what to know. Okay, so what did he have to do? He had to go to the library and he had to find the books on all this stuff, and he had to read and read and read and read to understand what he was supposed to know, to digest the information and to find the information. Ben Carson's story is the exact same thing. No one taught him how to do the operations that he did. He invented those operations. Well, then how did he know it? By reading about the human body, reading how things connected from each other. So that's not an excuse for this class, okay? That is literally a benefit to this class, that I'm making you guys read and process the information and giving you little hints along the way. And I apologize for not being there to give you little hints along the way for some of this chapter 3. So I'm going to go over a few things with you, but I'm not going to just overwhelm you with information. You processed, and look, you've been introduced to the terminology. You've been introduced to the ideas. Are you an expert at it? No. Okay, are you going to come and teach a class about it? No. Are you going to all of a sudden be an engineer because you read this information? No. But you are going to be introduced to it, more knowledge here and here and here, so that when you find what you're interested in, you can take the foundation of being introduced to these things and go further, okay? You're building a base for yourself. So don't get discouraged when you're like, what is going on? Okay, I don't know what this stuff is talking about. There's sometimes I have to read a few parts of this book 50 times before I'm like, okay, so wait 1 second, because people are talking around me or there's things going on and I have to read it out loud and really picture what is going on. And that's how science is, you guys, and it is good information if you get interested in it, okay? So look, I'm not going to go over things from page 80, define, identify, explain, because those are things you find right in the book. All you have to do is go look for the information. The apply section, tampoco. I'm going to just go into the problems, okay? Look at number 1. It says graph and add each of the following pairs of vectors. Displace, letter A. Let me turn my chair. Number 1, letter A. You have 6.3 miles north and 1.4 miles south. So you're going north 6.3 meters, south 1.4 meters. That's going to be negative, right? So when you add those together, it's just going to be 6.3 minus 1.4. So your answer should have been 4.9 newtons. I mean north, pardon, 4.9 to the north because you did more north than you did south, okay? Then letter B. It says velocities of 8 miles per hour, meters per second. Golly me, I think I'm just going to stop reading the units. 8 meters per second north. Okay, so what are you going to do? You're going to go north, 8. And then you go to the west, 6. Right? So give the approximate direction of the resultant. Well, the possible direction is going to be this. Right? Because you're going northwest. So you're really going that way, right? So, what do we need to do to find the displacement of this? You need to use your Pythagorean theorem. You need to use a squared plus b squared equals c squared. Remember, this is always c. Most of you guys have learned this in math class. So a squared is 8 squared is 64. B squared is 6 squared, 36, equals c squared. So now we have 100 equals c squared. To get the square off, we have to do the opposite, which is square root. So we square root the 100 and c equals 10, pardon. And that's the displacement of that one. Okay? Number 2 says calculate the magnitude of acceleration for the following velocity changes. Let me see if I wrote down the formula. Okay, acceleration is the change in velocity over the time. Okay, that's acceleration. You might have seen it as velocity final minus velocity initial over time, and that's the exact same thing. That's the change in velocity. So you have, for letter A, 50 meters per second forward to 35 meters per second forward. Okay, so what do you have? You went from the final is 35, and the initial is 50. That's your change all over your time, which was 4. So when you get that, you get negative 15 over 4, which means that you were decelerating, okay, not accelerating. You weren't going faster, you were decelerating at negative 3.57 meters per second. Letter B is 35 meters per second to 15, so now we're going to go 15 minus 35 all over 50. Okay, and when you do that, you should have gotten a negative 0.4. Number 3, we're going to skip. Number 4, somebody that I was grading there, Rebby's son did this, looking at it, drew a great picture, and I cannot draw a picture for this, okay? A piano is wheeled on a cart. A person on the left side is pushing it with a force of 65 north. A person on the left side, so they're on the left side, they kind of try to trick you on this. So they're pushing it this way, so they're pushing it to the right, okay? While a person on the right side is pushing with a force of 58. Well, guess what? This one's negative because it's going this way. This one's positive because it's going that way. Okay, and that was a little confusing in the book, but just to let you know that's how it goes. Draw a free body diagram, I can't, this is my free body diagram, of the piano and calculate the net force. Okay, so we go 65 minus 58, your net force is going to be 7 newtons. Okay, positive because this is positive and it's bigger. Okay, number 5, what is the mass of an object that has a weight of 45 newtons? Okay, so your formula that you're using for number 5 is the force of weight equals mass times gravity. Okay, mass times gravity. Well, we know the weight is 45 newtons, that's the force. Mass is what we're looking for, and gravity is 9.81. So we just divide that, okay? You're gonna find that in your book if you were reading about gravity, right? When you divide that out, it's gonna be 4.6 is your mass, okay? Let's see which one we're doing. Number 6? Yeah, number 6. It says, the first stage of the Saturn V, I guess is what they're trying to say, right? Saturn V rockets used to launch the Apollo manned missions to the moon produced a total thrust of 33.9 meganewtons. Meganewtons means that it's newtons times 10 to the 6. Okay, that's mega. That's what mega means. At launch, the entire rocket had a mass of 2.95 times 10 to the 6 kilograms. Draw a free body diagram of the rocket just after liftoff and then calculate its acceleration. If you want to see a good rocket diagram, you got to ask one of your compañeros. Okay, so the equation that we're going to be using here is force equals mass times acceleration. Okay, so the force is 33.9 times 10 to the 6. The mass was 2.95 times 10 to the 6. And then we're looking for the acceleration. So you're just going to divide this out, which is really nice because look what happens. You cancel that, right? And you're left with 33.9 divided by 2.95, and the answer is 11.49. Okay? Number 7 is interesting. There's actually no math there. That's why I want to mention this one. An object with a weight of 17 newtons is falling in air at a constant speed. What is the magnitude of the drag on the object? How do you know? Well, what's drag? Do you guys remember? It's air resistance. Okay, so it's a 17 Newton object falling in the air at a constant speed. Eso significa que there's zero acceleration. It's constant, okay? Now, we read in the chapter that, and we've talked about this before, if there was no such thing as air resistance, which is friction in the air, right? Everything would fall at the exact same rate, no matter if it was a feather, a rock, or anything like that, okay? It wouldn't matter. Because there was no air resistance to be stopping the object. Okay, but because there is air resistance, we have to calculate drag. Well, the calculating drag is actually very complicated, but not in this case because there's zero acceleration. So, guess what? When there is zero acceleration, the drag is equal to the weight of the object. So literally, your drag is 17. Okay, it's when there's zero acceleration, that means it's just falling at a constant speed. The drag is equal to the force going down. So it's 17 newtons going down, there's 17 newtons pushing up. And that's what's helping it fall at a constant speed. Okay, it equals itself out. Okay, looking at number, let's see, 11. 11 is the last one we're going to do today. What is the AMA of a simple machine that requires 50 Newton input to produce a 240 Newton output? Let's do that one first. AMA is really easy. It's it's force, output over force input. Okay, force output over force input is AMA, right? We talked about that in the last section. So that's going to be 240 over 50, which is going to give you 4.8. That's the first part of it. The second part is if the input distance is 1.6 meters and the output distance is 0.31 meters, what is the efficiency? Okay, efficiency is work output over work input. However, we don't know the work. It didn't tell us the work. It only told us the force and it told us the distance. So what do we have to do? We have to use the formula for work, which is what? Force times distance. Force times distance. So this is going to be the force output times the distance output over force input over distance input. Okay? Well, that's going to be 240 times 0.31 over 50 times 1.86. And when you do that, your answer is going to be 0.8, which means that we know it's in percentages for efficiency. It's 80% efficiency. Okay? And now we can move on to our chapter 4. Okay? So listen carefully to the temas that we're going to be talking about today. Thankfully on chapter 4, if you look at it, you will see that we have already studied these things. We studied this last year, okay? Together in class, not just by yourself in 4th quarter. So, we've read this quote before. I do want you to read the quote with me on page 82. Look what it says. This is Blaise Pascal. He was very influential in mathematics and in science. He said that the God whom Christians worship is not merely the divine author of geometric truths and the order of elements, but the God of Abraham and of Jacob. The God of the Christian is a God of love and of consolation. He is a God who fills the soul and the heart which he possesses. He is a God who makes them feel within their own misery, whose infinite grace unites itself with their inmost soul, fills it with humility and joy and confidence and love. It makes it impossible for them to seek any other end than himself. What's really influential about hearing a Christian scientist talk about that is that science is very dry sometimes, right? We think. But this man dedicated his life to studying mathematics, dedicated his life to studying science, and he came out with a knowledge of God and his love and his intimacy and his personality with us as human beings. Not some intelligent being that a lot of Christians like to say, that created the world. Not some distant God, but a God who cares about his creation and loves his creation. Which shows us that science doesn't have to be the answer en contra de Dios. Science is the answer of God because it's how he created the universe, with love. Okay, so let's look at the first paragraph. We're talking about fluid mechanics. So what is fluid mechanics? This is a great paragraph and I'm going to dissect it with you. Basic principles of mechanics like Newton's laws. You guys just studied the laws of motion. And the law of conservation of momentum apply to all states of matter. What are 3 states of matter? Liquid, solid, gas, right? And number 4, plasma. Okay, but we don't study that one a lot. Because liquids and gases are fluids, okay? We know that. Matter that has no definite shape and can flow, okay? It has no definite shape. Look, the air is a gas. There's no definite shape. I'm in it right now. You're in it right now, right? Liquid has no definite shape. What gives liquid its definite shape? The solid that it goes in, okay? The boundaries that we create with solids, okay? The liquid itself does not have a definite shape. They also have unique properties that solids do not have. Just as mechanics is the study of motion and forces in general, fluid mechanics is the study of motion and forces in fluids, okay? So that's what fluid mechanics is, the movement of fluid. That's all. Look at the kinetic theory of matter. You are going to do 5 sentences, and listen carefully, 5 sentences on the kinetic theory of matter and the different effects of cohesion on the states of matter. I'm going to explain what I mean by that. 5 sentences to define, in your own words, the kinetic theory of matter and how cohesion affects different states of matter. Okay, well, let's talk about that. We know that the kinetic theory of matter explains how molecules are always moving, okay? We look at a solid shape, doesn't matter what it is, we look at a solid shape and we say there's nothing moving in this solid shape, it's not alive, okay? It's just a shape. But the molecules are moving. Are they moving fast? Here in this solid? Absolutely not. But in the air, are the molecules moving fast? Absolutely yes. Because in solids, the objects are cool. The molecules are not moving very fast. And that is what gives it the opportunity to form a solid. Okay? Because, and we're going to talk about it with cohesion, that the molecules come together and stay together. Because they're cold molecules. So they don't have anywhere to go. But if you go into a liquid, what's going to happen? The molecules are going to be moving more. And you see activity in your water, in your juice, it doesn't matter. Things bubble up, right? Air gets stuck in it. There's a little bit of movement, and especially at the microscopic level, the molecules are vibrating, right? And then you go into the gas, and the molecules are just going crazy, okay? Because they don't stick together. Well, why aren't they sticking together? Because they have less cohesion. Remember what cohesion is. Look what it says in page 83. Atoms or molecules of the same substance are held together by an attraction called cohesion. Look at the diagram on 4.1, right? Cohesion means that there's an attraction. It's like an imán, a magnet between the same molecules. So if you have molecules in this liquid, those molecules are all the same liquid, so they're going to be sticking together, okay? And the temperature determines how much they're going to stick together, okay? Because the cohesion has effect and has relation to the temperature. So it says the faster atoms or molecules are moving, the less they are affected by cohesion. According to the kinetic theory, molecules in a warm object move faster than molecules in a cool object. Therefore, the molecules of the warm object stick together less readily than do molecules of the cool object. So that's why you can melt things, right? You can melt certain substances because if you put heat to them, their molecules start to move faster and they can't be cohesive. They can't be stuck together. So they have to move out and expand, and they turn into a liquid and then a gas. Okay? That's what happens with water. That's why water will change different forms as well, because the cohesion all of a sudden becomes ineffective. So that's all I'm going to say about that one. Okay? Then you need 2 sentences on adhesion. Remember, cohesion is where molecules that are the same stick together. Adhesion is where molecules that are different are attracted to each other, okay? So you look at the picture here. Cohesion is bringing the water together. Adhesion is keeping the water stuck to the faucet because there is a force between the metal and the water where the water doesn't want to let go yet. That's adhesion. Remember, let me see. It's also going to affect capillary action. But right here, remember this picture we talked about last year? Cohesion is keeping the water together in this tube, but adhesion is pulling the water up a little bit because the force of adhesion between the glass of the tube and the water is stronger than the force of cohesion between the water molecules. So the water molecules are more attracted to the glass than they are attracted to each other, which makes the water push up, trying to hold on to the glass instead of hold on to each other. In mercury, it's the opposite. Mercury has a stronger cohesion force and a smaller adhesion force, so it pushes the water up in a dome shape, pushes water down, the mercury down, perdón, trying to hold on to it so that the glass can't agarrarlo, okay? So that's when adhesion is less than cohesion, and it creates a capillary action, which we're going to talk about in a second. Look on page 84. You need to give me 3 sentences about surface tension. Remember, surface tension is when if you have water and you can put stuff on top of it, a paper clip, a little bug, and different stuff like that, it's because the cohesion is so strong that it's forming like a surface over the water so that things can sit on it. You might see let's say you have like dirt in your house and you leave the water bottle open. When you get up in the morning, you pour yourself some water. If you leave that water there, all those little things are gonna float up to the top and they're gonna stay there because there's gonna be a surface over that water where the cohesion is helping there create a little film over it, okay? But even one little push of the water and that surface is gonna go away because the cohesion has been scrambled up. So what is surface tension? And then you need 4 sentences on capillarity. Okay, capillarity is when this happens in plants. I did an experiment on this, I told you guys before, where you take, the flowers and you stick the flowers in colored water and you watch the force of gravity push the water down and push it into the flower. And when it's in the flower, there's adhesion working to where the stem of the flower is grabbing the water molecules and continues to grab it up its sides where it pushes that water up into a capillary action, okay? And you can see it by the change of the color of the flower because you put blue dye in the water or anything like that to see what it does. That adhesion helps you grab things to different substances, grab water to different substances and push it up. Okay, until it goes up slowly, but the adhesion is working to push it up little by little, while the cohesion is trying to work against it, okay, which makes it a slow process. So give me 4 sentences about that. And then the very last thing for today is give me 3 sentences about pressure in liquids, okay? You're gonna stop right there. Pressure in liquids. You're gonna stop right at this example. I'm gonna show you this example and then we're gonna be good to go. But look what it says in the first paragraph about definition of pressure. If you have swum to the bottom of the lake or a deep pool, you may have felt as if your chest and eardrums were being squeezed. So like it's so heavy down at the bottom of a pool or an ocean or anything like that. It's because the water has what? Weight. It has a lot of pressure. So how do you find pressure? Look at the equation on 85. Pressure is force over area with the unit of pascals. Look at that, the guy that was just talking. Okay, it was named after him. So look at example 4.1. A force of 150 newtons is spread out over an area of 4 meters squared. What is the pressure exerted by the force on the area? Well, it's just 150 over 4 because it's force over area, which means that anywhere in that one area of the 4 meters, there is 37.5 newtons per square meter being pushed down. So 38 pascals being pushed down on you if you're in that water. Okay, there you go. I know this was a long video today, but it was important information. So now you get to do your science homework. Bye.